Thank you, Tom, for the introduction, and thank you for inviting me to speak here. So I'll talk about the quantitative theory of Gowers norms, which is already discussed in many talks. First day, but I'll focus on a different aspect of such results, namely what sort of applications there are to analytic number theory, as well as to some problems in ergodic theory. So let's start with by now familiar definitions. So we want to define the UKN Gowers norm of a function. So first define the unnormalized Gowers norm of a function with finite support as the sum over parallel pipets of your function. And then if you have a function on the interval n, you define the UKN norm by this formula in terms of the unnormalized Gowers norm normalized by the Gowers norm of the interval. So then we have the inverse theorem for the Gowers norms, originally proven by Ziegler. Then Freddie Manners had the first quantitative version, and then we have the link from Joni quasi-polynomial inverse theorem. So just to recall, if a one-bounded function has a large Gowers norm bigger than delta, then your function needs to have correlation at least quasi-polynomial in delta with a nil sequence coming from a manifold of step at most k minus 1, and they're bounds on the complexity and dimension. So what's really great about quasi-polynomial bounds is that if you iterate them, they remain the same. So if you compose two quasi-polynomials, you still have a quasi-polynomial, which is the same for polynomials, which is really helpful, for example, when Leng's and Joni applied their result to prove stronger bounds for sets lacking K-term progressions. Result. So for many purposes, the quasi-polynomial bound is almost as good as if you had a polynomial bound. And so in this talk, I want to discuss some avenues enabled by this new quasi-polynomial result of Leng's and Joni. So there are various things one can do with this. One is you actually get a slightly simpler approach to proving Gowers uniformity of arithmetic functions. Even if you only care about quantitative bounds, you actually get to avoid some steps by working with this stronger inverse theorem. So I mentioned that. Then secondly, it allows one to sort of build a quantitative version of the many of the results of higher order Fourier analysis of the primes, for example, which for a long time were mostly qualitative or with very big bounds. And thirdly, kind of curiously, there are some purely qualitative results in ergodic theory, where it's actually, for the proof, it's very useful to have strong quantitative bounds on the Gowers norms. So I'll mention some applications like that as well. Okay, so let's start with the first point. So how do we prove Gauss uniformity of the primes, for example, given the quasi-polynomial inverse theorem? So of course, the Gauss uniformity of the primes is the starting point of if you want to do anything relating to how to Fourier analysis of the primes. Theorem said the following. So the original version was the Ziegler Gauss uniformity of primes. Then using Manners' inverse theorem, a few years ago, Terry and I made it quantitative with double logarithmic bounds. And then recently, Jane Fleming made it quantitative with arbitrary power of logarithm savings, which is the best you can hope for given the current knowledge about the primes using the quasi-polynomial inverse theorem. So what this states is if you define this kind of Cronmary model for the primes, which Terry also hinted at in his talk, that if you so you want to model the primes by something which has the same mean value and also the same mean value in progressions. So what you could do, you could note that the primes don't have small prime factors. Let's say there are no prime factors less than w for all but small number of primes. So you could compare the primes to this lambda w, which is the indicator of w rough numbers, but then you need to renormalize it so that it has mean value 1. So then you get this function lambda w, which is much simpler to work with than the polynomial function itself. So we understand fully, let's say, correlations of this function. So we almost any property of this function we can understand sort of directly. And take some value of w, for example, this value e to the log to 1/10. It's not too important which value, as long as it's not too small. Then if you look at lambda minus lambda w, that's Gowers uniform with polar logarithmic bounds. So the quantitative version is sometimes done with the w trick instead of the introducing this lambda w, but for quantitative bounds, it's better to introduce this primary model and then compare the primes to the primary model. This is easy to deal with. So this, for example, quite directly enabled Lang to give good bounds on linear equations to primes. So the Joni Tera theorem, because if you, for example, counting k-time progressions into primes, because we have this generalized for Neumann theorem, we have this Gauss uniformity bound, we can just replace the count weighted by the Polynomial function by the count weighted by the primary model. And then we're counting rough numbers and progressions, which can be done using C theory with very good error terms. So, so then you get good bounds on the number of linear equations in the primes. Okay, so how does one go about proving this result? So the original Joni Tera approach was the following. So if we assume, to count positive, that the UK norm of lambda minus lambda w is large, then you would like to apply the inverse theorem. But the inverse theorem is only for bounded functions, so you have to get around that. And they did get around that by introducing two ideas. So one is they could transfer the inverse theorem from bounded functions to actually unbounded functions, as long as those unbounded functions were manageable in the sense that there's a pseudo-random majorand for them. And secondly, they constructed a pseudo-random majorand for the primes and show that indeed it satisfies the kind of functions you need. So kind of you have to look at the correlations of this pseudo-random majorand, and then they could apply the inverse theorem. And then it reduces matters to looking at correlations of lambda minus lambda w with nil sequences. And then you go further from there. So this is, of course, a very ingenious approach, but given the new Gauss-Polynomial inverse theorem, one can do something simpler and actually avoid the first two steps, which take some work, especially the second one, where you need to construct this pseudo-random measure and prove this pseudo-random. So now if you want to, so if we suppose that the Gauss norm of lambda lambda w is bigger than log to the minus a, well, you can just divide by the upper bound for this function, which is log n. Then you have a bounded function. And then on this bounded function, you can now apply the inverse theorem. And it's not too costly to lose this factor of log because of the good bounds on the inverse theorem. So you get that lambda minus lambda w that's correlating with the nil sequence by an amount which is quasi-polynomial logarithm. And so what's known about the Polynomial function is it can be written as a sum of so-called type 1 and type 2 sums. So there's one identity which allows you to write the Polynomial function as some of this kind of divisor sums as well as bilinear sums. And we understand both the divisor sums and bilinear sums of nil sequences. So you can apply Cauchy-Schwarz to get rid of the coefficients, and then use the Ergodic distribution theory that Benateri developed.
Is that strictly true, or do you need Lang's quantitative refinements of that?
Yeah, you need the quantitative refinements. Actually, yeah, that's true. Yeah. Yeah, because you have large dimensions and things like that. Yeah, thanks. That's a good point. So we do have type 2 estimates from the sequences, which basically tell you that the only way something like this could happen is if the new sequence is more or less periodic with not too large a period. So a period of comparable size to this number. So by passing to the modulus of period, you conclude that lambda minus the model has large mean value, some progression, some modulus. And by this amount, and now if we had this generalized Riemann hypotheses, we could conclude directly because we would have square root bounds for the number of primes, and we also have a very good understanding of this model function. So we have good asymptotic for how many integers there are in progressions weighted by this function. However, we don't have the generalized Riemann hypotheses, so we need to do something else. And the problem is that you cannot just use the Ziegler-Wolff theorem, which would be, the standard result about primes and progressions, because it would save you a large part of log, but you need to save a little bit more here. So this doesn't come up if one wants weaker bounds, but here it does if you want good bounds. So how to get around that? So this issue already appeared in the work of Terry and I, and we overcame it in the following way. So kind of as Terry already mentioned in this talk, Ziegler zeros, they could bias distribution of primes, but we can then insert a correction term to this model to take into account the possible influence of the Ziegler zeros and get a better error term. So if there is a Ziegler zero, so a real zero beta of corresponding to a Dirichlet character chi mod q, then you can correct this Cronmer model by this amount, so chi n into b minus 1, to kind of counteract the influence of the zero on the explicit formula for the primes. And then there's an old result of Landau and Page, which says that with this this correction term, so the Ziegler term, you actually get much better bounds. So quasi-polynomial bounds on the number of primes and progressions. And so what this means is that if we were working from the beginning with the function lambda minus the Ziegler model, we could run the argument. So in the end, we have good enough bounds for this function in progressions, and we can conclude that lambda minus the Ziegler model has good bounds for the Gowers norms. And then, okay, so we introduce the Ziegler zero, but then you want to get rid of it. So that actually the contribution of it is negligible on the Gowers norm side. So by the triangle inequality for the Gowers norms, what we want to do is show that the primary model is actually closer to the Ziegler model. Because then you could replace the Ziegler model by the primary model and get the result that you want. So the difference between these two functions is chi n to the beta minus 1. And n to the beta minus 1 is a slowly varying smooth function. It doesn't really matter too much. Let's just ignore it. Let's pretend that the difference is chi n. Then what we want to understand are the UK norms of this character chi. And so what we know about this expression, because chi is multiplicative, is that these are sums of chi of some polynomial. Yeah?
There should be like a few conjugates there, right?
Yeah, but chi is real, so this character always has to be real because it's a Ziegler character. Yeah, but otherwise it would have to be. So this is chi of some polynomial of degree 2 to the k, and we have good bounds on character sums over polynomials. So this is the Weil bound, which gives essentially square root cancellation, as long as this polynomial is not a square, because if it's a square, then there's no cancellation. So using this, you can get good bounds on the Gauss norm of this character, which is decay like a power of the modulus. And from Siegel's bound, we know that if there is this exceptional modulus, it needs to be relatively large, so it needs to be larger than any power of log. And if you plug it in, you get a good bound on this error term, and then you conclude the proof. Okay, so that's in a nutshell how you can use this quasi-polynomial inverse theorem to prove Gauss uniformity of the primes. And you can sort of see from the proof that it wasn't so much specific to the primes. You could have a more general recipe of doing the same thing. If you have some other interesting arithmetic function whose Gauss numbers you want to understand, you could try to apply the same techniques. And in fact, that's been done many cases in the qualitative setting, but now you could do it quantitatively. So if you take some sufficiently nice arithmetic function, things like the divisor function or the representative function of sum of two squares or the Möbius function. The Möbius function is a bit easier because it's a bounded function. But so what you want to do is first you want to find some model function for your function, which has the same behavior in arithmetic progressions, such as we had with the Cromwell model or the Siegel model. And this usually is not too difficult to come up with, just sort of looking at the distribution of your function in progressions. And then, so these functions, again, they may not be bounded, they may be bounded by a power of logarithm, but in practice, they will be bounded by a power of the divisor function, if there's anything naturally occurring. And although the divisor function is not bounded by a power of log, it is bounded by a power of log outside a very small set. So there are very good exceptional set bounds for how often the divisor function is large. So you could say that these functions are less than a large power of log outside a negligible set, which is constant A is large. And then you can essentially pretend that these functions are bounded by log n to the A because the exceptional set is so small. And then you apply the quasi-polynomial inverse theorem to the function f minus the module divided by this large power of log, which is now essentially a bounded function. And then you run the same argument, and in practice, again, there's some kind of decomposition of these functions into type 1 and type 2 sums, if there's anything naturally occurring, like these functions here, for example. In this case, you can again use the equidistribution theory of nil sequences to conclude your argument. So that's kind of a general recipe, which I think in the quantitative setting has maybe only been done for the primes and the Möbius function, but it could now be done for other functions as well. And you can avoid the pseudo-random measures in this process at the same time. Are there any questions at this point? Okay, so let's switch to the other topic I mentioned. So quantitative bounds in higher order Fourier analysis. So originally, most of the results about higher order Fourier analysis of the primes, for example, were purely qualitative. But now one could take many of these statements. So here's a sample of 3 nice results, and one could try to input the quantitative inverse theorem to their proofs. And hopefully, if one gets lucky, one can recover a good quantitative bound. It's not always so easy, but turns out one can do things. So there's a sample of 3 theorems. So we have the asymptotics for linear patterns in primes, which Green-Ziegler prove. We have also asymptotics for polynomial patterns in the primes, which Ziegler proved. And also we know that in positive density sets, you can find K-ten progressions where the difference of your progression is a shifted prime. So this was proved originally by Franciscan Host and Kra, assuming the Gaussian uniformity of the primes, and then an unconditional proof was given by William Ziegler. So as I already mentioned, the first one was quantified by James. The third one we quantified with Terry, with some bounds which you save a triple logarithm in the density if you use the improved bounds for the Neumann theorem for K-10 progressions. But it's also natural to look at the second problem. So what about polynomial patterns into primes, since we now understand quantitative results about linear patterns into primes? So here that's the theorem of Ziegler, and with William Mathieson and Mengli Wong, we quantified this. So if you have a collection of polynomials of degree at most d, you need to make this assumption, which is the same as in the work of Ziegler, that so essentially this says that the polynomials are of degree d and the leading coefficients are distinct. So you have distinct leading coefficients of these polynomials of degree d. Then if you look at how often you find this kind of k-term polynomial progression within the primes, you get the expected asymptotic, which is some sort of local product, and then you save an arbitrary power of logarithm, which again is the best you could hope for with current technology. So we can also get a similar result for the Möbius function. In fact, for a slightly larger class of polynomials, slightly weaker assumption on the polynomials in that case, but doesn't quite cover all the polynomials. But actually for the Möbius function in the qualitative setting, the result was known for all polynomials, where the difference between any two polynomials is non-constant. So this is actually using things related to Charles conjecture, kind of, so high order uniformity conjecture, and progress we made on that with mathematical recipe, Tau and Ziegler. But for the prime case, this assumption is the same as qualitative works. Okay, so how did we go about proving this result? So let's just focus on the model case. Let's say we have a 3-term progression with polynomials 0, m squared, and 2m squared. So again, you want to kind of, since we know that the polynomial function minus the Ziegler model is very strongly Gowers uniform, you kind of want to introduce the Ziegler model here and then some correction terms. So kind of it's kind of decomposition. So you can decompose the polynomial function as the Ziegler model, some parameter wj. Turns out we need different parameters and some error term. And if you do this, you get the expected main term, then you only have the Ziegler model contributions, and you get 7 more terms. Just a kind of a representative case is this one. So there are other cases, but either they are similar or simpler to deal with. So let's say you have on the first and the third function, you have the Ziegler model, and the second function, you have the error term, for which we have good Gowers norm bounds. Okay, so so how do we bound the error term here? Okay, so just to recall the definition of this Ziegler model, it was the primary model times this correction factor involving the possible Ziegler 0. And if you just write it out, and if you use Möbius inversion on the condition that your numbers are co-prime, and you truncate this sum, which you can do with small error, basically because of the density of smooth numbers, you can write your sum as this kind of expression. So it looks a bit nasty, but the point is that this d sum does not go very far, so it goes only a bit above this parameter w3. So w3 to some power is not too large. You can truncate it like that, and the error term is small in L1 norm. So if you plug this in the third function, you get this lambda w3, and if you replace it by this function and ignore these multiplicative factors, kind of the only thing that matters is this divisibility condition. So you plug that in there, and for every d, you need to get a bound that saves log into the minus a divided by d. So now you kind of got rid of the third function, and you only have 2 functions left. So it's kind of an inductive argument. And now we use a generalized Neumann theorem for these polynomial progressions due to Pelouse, which allows you to bound this average in terms of the some Gowers norm of the final function in this progression. And so there's some dependence on these coefficients, but it's actually very benign. It's polynomial dependence. So if we split these variables n and m into progressions modulo d, we get some coefficients on the polynomials depending on d, but they only have a polynomial influence. So so you can bound this sum here in terms of d to some power, and then the some Gauss norm of the error term. And for this error term, which was the Polynomial minus the Siegel model, we have very good bounds on the Gauss norms now. So we save a quasi-polynomial amount there. So then you just need to balance your parameters. You make sure that W2 is large enough in terms of W3, and then you get something small. And the other terms are handled similarly. So you need to also make sure that W1 is large enough in terms of W2. So this is the reason that the parameters remain the same, that you kind of have this kind of bound in the end. So if W3 was equal to W2, it would not be good enough. But if you take W2 a bit bigger than W3, then you can make it work. So that was kind of a trick there. So then you're left with the main term, so the Siegel term. And there you really expect that the main term comes from the primary model, not from the Siegel part. So you can extract the primary model part, and then you're left with several other terms, such as this one, all involving the character. And so these primary model terms you can estimate using basic Sieve theory. So the fundamental lemma gives you good asymptotics. And the parts with the characters, using again character sum bounds, you get good cancellation on these, which save a factor of any negative power of log. So these are kind of secondary main terms, which save an arbitrary power of log compared to these main terms. And these main terms give you the local products that were in the main term of the main theorem. Yeah, so that's how you prove it. Any questions on this one? And yeah, so there are other. You can basically try to take any statement in higher Fourier analysis of the primes and try to make it quantitative, and I would assume that usually you can, but not too many cases have been handled yet. But using kind of similar techniques, there's a good chance that many of these results could now be made quantitative. So then let's switch to another topic, which is the third one I mentioned. So how do these quantitative bounds have something to do with ergodic? So how can you use them in a problem in ergodic theory? So kind of relating to the talks on Tuesday, some of them. So the setup is that you take a method preserving system and take some polynomials, and there's this influential conjecture of Westenberg, Bergerson, and Leibman about multiple ergodic averages. So if you take this multiple ergodic average with polynomial iterates, P1 after pk, then it's conjectured that these always converge pointwise almost everywhere. So this limit should exist. So if you only have one linear polynomial, this would be Berggraf's ergodic theorem. But any other case turns out to be quite hard. And the only known cases to date are when you have at most two polynomials. And if you have two polynomials, then one of them needs to have degree 1. So these are due to results of Bourgain and one recent result of Frostmaker and Tau, which are the case of two polynomials, one of which is linear. And so, of course, L2 convergence is easier than pointwise convergence, and results of Host and Gra and Leibman actually solve the L2 version of conjecture. So we do know that in L2, these averages converge, but the pointwise question is harder. And in most cases, it still remains open. Okay, so how can we make this problem a bit more number theoretic? Well, you could also introduce some weight on the sum. So not look at sum over all the integers, but the sum over the integers with a given weight. And see what happens for those averages. And indeed, so you could, for example, add the Möbius weight. So that's a natural way to add. Or weight that. So it's number theoretically nice. And in that case, I could prove the analog of the Furstenberg-Leibman conjecture with the Möbius weight. And so actually, initially, I had a version of this paper with assumed that the polynomials have distinct degrees, but then using the Lenz-Rochoni inverse theorem, I can have any polynomials. So this update should appear in the archive in a few days or so. This relates to a problem that Frank Ignatis posed. So he posed the case of if you have mu of n, f1 t to the nx, f2 t to the 2nx, so two linear polynomials, and he proved that these averages converge. Also, you could handle very likely commuting transformations instead of a single transformation, and you also get a decay rate because the bounds we're going to use are quantitative, so they actually imply that not only this goes to 0, but it goes to 0 with logarithmic speed. Okay, so you could also ask, what if you had some other arithmetic weight, and the other natural weight take would be the primes. What about Ergodic averages over the primes? So in ongoing work with Krauss, Savi, and Tao, we'll be looking at that. And so we can have the case of two transformations, one of which is with a linear polynomial, and the other one is with a nonlinear polynomial. So this is kind of the analog of the Krauss-Merck-Tau result, but over the primes, I don't know, with the integers. And of course, for the primes, you cannot hope to do anything better than for the integers, because the primes have non-zero mean value, and so on. So you can only hope to handle cases that are known for the integers. And we need to use the machinery that Krauss-Merck and Tau developed for the integer case in particular. Okay, but how does all of this relate to Gowers now? So where do they come into play? Let's say in terms of the Möbius result. So let me sketch how the Möbius result is proven. So let's look at this ergodic average up to n. And let's say we have some boundary functions. So first I want to say that it suffices to consider this average not at every point, but in a sequence of n's that grows exponentially. And that's because these averages vary slowly. So because these functions are bounded, if you take the average up to 1 plus epsilon n, it's almost the same as taking the average up to n. That's using the boundedness of the functions. Which means that it suffices to consider values of n that are powers of some number bigger than 1. So you get kind of a smaller set of points to sample in. And let's say for simplicity that it suffices to sample these averages as powers of 2. In reality, you have to take, instead of 2, 1 plus epsilon, but it's the same argument. Okay, so now we want to understand these averages at powers of 2. So the length of the sum is a power of 2. Okay, so we want to understand how often these averages are large, let's say begin on epsilon, and using semi-stationary inequality, we can relate this to the mean square of this ergodic average. And so now, if we had a good bound on the mean square of the ergodic average, we saved more than one logarithm, let's say 2 logarithms, then what you could do, you could apply the Cantelli theorem, because so we're sampling over these points 2 to the j, and 1 over log 2 to the j squared converges. So then using only these 2 facts, you conclude that the set of points where the average doesn't go to 0 has measure 0. Okay, so in this way, we reduce the problem to strong quantitative bounds of this kind of L2 means of ergodic averages. Okay, so now quantitative aspects start to show. And how do we get Gowers norms out of this? So here I've just repeated the statement from the previous slide. So now we kind of want to apply duality. So, so the absolute value of a squared is the same as a times a bar. So it suffices to show that if you take the integral of a times other function, which turns out to be a bar, but you can just think of it being an arbitrary function, which is bounded, then you want to save a power of log n on this average. So phi should be a bar, but actually it doesn't really matter what phi is. So let's just treat it as a completely arbitrary function, kind of a duality argument. And now we use the fact that the transformation is method preserving. So it means that in this integral, you can make transformations. X goes to t to the mx for any m. And in particular, you can average such transformations on the integral. So actually, the integral is exactly the same as if you shift these x's. So you replace x by t to the mx, and you average over m, and you also have this average over n here.
Are you missing the Mobius function there?
Oh yeah, of course, yeah. This would be a Mobius of n, yeah. So on this quantity, you want to have a bound which saves 2 logarithms. And now, at this point, you completely forget about the ergodic theory, and you've reduced the problem to analytic combinatorics problem by forgetting any information you had about these functions. So here we have an average of the form Mobius of n, should be here, times some bounded functions at the points m must be 1n up to m must be kn. We don't really care at all what these functions are, it's just one bounded. So all the ergodic theory has disappeared at this point, and it's a problem about this kind of polynomial counting operators. Okay, so we want a good upper bound on this, using the fact that the Mobius function is strongly Gauss uniform.
The correspondence principle in the opposite direction, the way it's normally done.
Yeah, essentially, yeah. It's really that, yeah. So it turns out that using repeated applications of the van der Corput inequality and the polynomial exhaustion technique induction, you can prove that averages of this form are always bounded by Gowers norm of some order, the first function, so the Mobius function. Okay, so in the qualitative setting, this is standard, but we need to care about also the quantitative bounds, that this is polynomial dependence on the Gowers theory. In the end, we need to get something quantitative out of this.
Do you need quantitative concatenation theory to make this work?
No, it's simpler than that. It's really just sort of repeat applications of van der Corput to get bigger and bigger families of polynomials. But I mean, there's this kind of semi-invariant that decreases. I mean, the one that comes in the PET induction, and at the very end you get to linear polynomials, and then you can apply the
Over short ranges, right? You don't get to. Oh, hang on.
This is like.
N is the tiny variable. Oh, you're lucky. Okay. Yeah. All right.
Yeah, that's
okay.
right.
All right. Fine. Nice.
Okay, and then we input something that length proved. So not only for the primes, but also for the Mobius function. we have strongly logarithmic bounds on the Gowers norms, and you just input it here, and so you have some small power here, CS, but it doesn't matter because you save an arbitrary power of log here, and the numeric just works out fine, and you save 2 logarithms or 100 logarithms for that matter, and that's how you prove it. So it's actually a second approach, which I had previously before I had this strong inverse theorem, which okay, so it doesn't quite give you the full result. It only works for distinct degree polynomials, but it is useful for something else. So so you could also look at other multiple functions, the Möbius function, about which we have less information. So let's say multiple functions satisfying the Ziegler-Wolffish assumption, and so for such functions it turns out to be the previous approach doesn't quite work, but this other approach, which is to actually bound these polynomial averages in terms of a weaker norm than the Gowers norm. So this is little u as norm, which captures the correlations of your function with the polynomial phase of degree at most x-1. So of course this norm is weaker than the Gowers norm, because it's only about correlations of the of your function with polynomial phases rather than with nil sequences. So for any s bigger than 2, this is a weaker norm. The little u2 norm is almost the same as the capital U2 norm up to some polynomial losses, but as soon as s is at least 3, it's a weaker norm. So it's better if you can control things in terms of this norm. And in particular, what's nice about this little us norm is that it's much easier to prove norm bounds, let's say for the Möbius function, for this norm than for the Gauss norm, because then you're looking at correlations of Möbius with polynomial exponential phases, and those were handled in very old work related to the Warren-Goldbach problem, essentially by Vinogradov. Maybe he didn't exactly state it, but his methods would work for this problem. So the kind of bilinear methods that he introduced. So smaller elementary, you don't need the actually the inverse theorem or sequences. And okay, so what is the sort of generalized polynomial theorem that's powering this? Is that if you have bounded functions, so theta now here plays a role that the Möbius function had previously. It could be any bounded function. You can always bound this in terms of the little u k+1 norm of the weight theta. Okay, which yeah, I haven't really seen other cases where you could use a weaker norm than the Gauss norm. But yeah, so so in a nutshell, how you prove this? Okay, so if you didn't have to weight theta on this, and so it's important here that the polynomials have distinct degrees. It's an assumption we didn't have to do with the other approach, but here it's very crucial that the polynomials have distinct degrees. So if you didn't have the weight on this, then there's Sarah's result about such averages, which says that you could control it in terms of the average of this function g1 with short intervals. And you kind of want to apply that theorem somewhere in proof. So you do induction on k. So if k is 1, then you have only one non-trivial polynomial here, and you can apply classical Fourier analysis to control this pattern. You can bound it by the little u2 norm of the weight theta. Okay, so then you do induction, and so you first apply one corput on the m variable. So they kind of discrete derivatives in the m direction, which eliminates this function theta because it only depends on n. So then you get in a situation where you can apply Sarah's inverse theorem, and you can conclude that this differentiated function is locally constant for many values of h. So if the differentiated function is essentially constant, it means that the original function is essentially linear. So so g1 is locally a linear phase. A bit like in Florian's talk, you had these local nil sequences. Yeah. Similarly, a local linear function here. So you got some information about this. And then if you do a bit of more tricks with corput, you have to get that this the phases that appear in the Z1 are major arc phases. So in every short interval, the phase is some rational number with small denominator. And since there are not too many rational numbers with small denominator, you can pigeonhole and pass to a single denominator to get correlation with a global major arc phase. So this is kind of problem initially that you have this local phase, but now you can make it global. And now, essentially what this means is that you can replace G1 by this E of alpha n. And if you do that, things factor out. You get the E of alpha m separately and E of alpha p1n separately, which goes into this theta weight. And then you've effectively reduced the number of polynomials by 1 with the change of variables on this theta, and then you apply induction to conclude. Okay, so that's how you prove it. And finally, about the prime multiple ergodic theorem, I'll just briefly say that there are 3 ingredients. So here also we use the little u norm, actually, the capital U Gowers norm, but we need it bounds on the little u Gowers norm of the primes, and so we need kind of similar techniques that's in the work of cross-mercantile, but over the primes. So for example, they used Sarah's inverse theorem. We inverse of it over the primes, which turns out we can prove with some transference arguments. Then we need some LP impermanent estimates, which they had for over the integers. We need them over the primes. And finally, there's this major minor arc analysis with the adults in the argument, which also we need to carry through in a slightly modified version with the primes, but it turns out these things work out. So that's in a nutshell how it is. Thanks a lot.